mathematicians! This is lesson 8.7, exponential functions for algebra. I thought you might get a kick out of my excitement because I know you are not excited, but I am. Exponential functions. Now, we have learned about linear functions, and linear functions were all straight lines, okay? Now we're going to learn about exponential functions, and in this we have this word, exponents. So anytime you see anything with an exponent, like this, 2 to the x power or 0.5 to the x, those are exponential functions. And if you notice in linear functions, they were just a straight line. They constantly went up at the same amount. They have this nice slope that's all the same. Exponential functions are where you kind of start slow and then you increase very rapidly because you're increasing by an exponent. Like if I were to do 2, then 2 squared is 4. 2 to the third is 8. 2 to the fourth is 16, and 2 to the fifth is 32. So my numbers go up quite rapidly in exponential functions. So what they're going to ask you to do is evaluate each exponential function for a domain. So this one, they give us the domain. So what that means is you're going to draw a table. You're going to have an x and a y. Those are my x's that they're giving me, -2, 0, and 3. And then you're just plugging them in for x. So 4 to the -2 power is 0.0625. 4 to the 0 power is 1. And 4 to the third power is 64. So that's it. When it tells you to evaluate it, this is what you need to do. So try B and C. All right, so for B, I have my table. So I'm going to do 5 to the -2 power. And I get 0.04. Oh, and then I have to times that by 10. You're always going to do your exponents first, so then you get 0.4. 5 to the 0 power is 1 times 10 is 10. And 5 to the third power times 10 is 1250. So if you look at this one, just in 5 numbers from -2 to 3, it jumps rapidly from 0.4 to 10 to 1250. So it's quite a big increase. So for this one, I have my domain and my range. So 3 to the -2 power is 0.11 repeating. Oh, and then I have to times it by -2, which is -0.2 repeating. 3 to the 0 power is 1 times -2 is -2. 3 to the third power times -2 is -54. So, real world problem. Suppose 20 rabbits are taken to an island. The rabbit population then triples every half hour. The function 20 times 3 to the x, where x is the number of half-year periods, models this situation. How many rabbits would there be after 2 years? So, in all these exponential functions, you want to make sure that you know that this is where they start. This is what they're starting with, 20 rabbits, okay? And this is what's happening, how they're growing. This is their growth rate. So they are tripling. It said it right here, triples, okay? Now, I have this equation, and to figure this out, they're just going to put in what they wanted. How many rabbits would there be after 2 years? Now, they didn't put 2 right here because they triple every half year. If you remember from this story problem, they triple every half year. So they would triple 4 times. So that's why they put a 4 in there. And then there would be 1,620 rabbits. If anybody deer hunts, this is the reason that they allow deer hunting. It's because it's very similar to this. They have these deer in our population and they reproduce quite rapidly. So then if we didn't do anything about it, we would have massive numbers of deer running around and getting hit by cars and so on. So they allow hunting. Same thing with geese and all of that. So try number 2. Suppose 10 animals are taken to an island and then the population of these animals quadruples every year. So use that function. How many animals would there be after 6 years? So I have my function 10 times 4 to the x power. And I'm going to put in, it triples every year. So I'm going to just put in a 6 for x. So you're going to do 4 to the 6th power, which is 4,096, and you're going to times that by 10. So you get 40,960. After 6 years, you only went with 10, and you end up with 40,000. It's quite a massive amount. Now, here is what the graphs will look like. This is a positive graph. It's going to start here, and it's going to go up, and then it goes up quite drastically after it hits the first couple numbers. This is another type. If you look, this is where my growth factor is greater than 1, and here is where my growth factor is less than 1. It goes the opposite direction. And then the blue are both negative. So this is if the growth factor is negative, greater than 1. And this is if the growth factor is negative, less than 1. So it just says right here, to graph an exponential function, make a table, plot the points, then join the points to form a smooth curve. So all exponential functions will have this curve. So graph each exponential function. So try these 2 functions. Okay, so I'm going to get some graph paper. There's the first one, here's the second one. Okay, well maybe I'm just going to use one graph for both of them because I need some space to do my tables. So I'm going to do this table over here, x and y. Now, when you do your tables, you're going to want to have negative numbers too, just so you get the full range. So let's do -2, 0, and 3, just like they gave us before. So 2 to the -2 power is 0.25 times 0.5 is 0.125. 2 to the 0 power is 1 times 0.5 is 0.5. 2 to the 3rd power is 8 times 1/2 is 4. So if I were to graph this, I'd go -2 up a tiny, tiny amount. 0 up 1/2, and then 3 up 4. So if you see, this is a tiny, nice little curve. Now, the thing to know about exponential functions is they will never hit the x-axis. It will just keep getting smaller and smaller and smaller, but it will never reach 0. Because if I started with 0 rabbits, would I have anything after that? No. You can't start with 0 of anything and multiply it exponentially. It doesn't work. So it always starts, that's just like the power of 0 is 1. It's the same type of concept. You can't ever get down to 0. So there's my green graph. Now here's the other one. X and Y. I'm going to have -2, 0, and 3. So 2 to the -2 power is 0.25 times -0.5 is -125. So it's really the exact same thing, except it's just making it negative when you times that by that. So 0.5, or this is -0.5, and this is -4. So notice, these are my starting points. Okay? So -2, -1.25, 0, -0.5, and 3, -4. And I have the same graph, but it's going down. So that first number, your starting point, tells you if the graph is going to be a positive graph or the graph is going to be a negative graph. Positive graphs like this one have a positive number and they're going up. Negative graphs like this one have a negative and they're going down. So many photocopiers will allow you to choose how large you want an image to be. The function f of x equals 1.5 to the x power models the new size of an image being copied over and over at 150%, where x is the number of enlargements. Graph the function. So here's what they did. They made a table, and then they kept graphing it, and then you can see if I were to connect these dots, it's going in our nice little curve that we have. So try A. You can also make images that are smaller than the original on a photocopier. The function 0.9x models the new size of an image being reduced. So an image is getting smaller. So it says graph the function. So let's use the same numbers that they did. 1, 2, 3. We'll just do 3. And let's graph it. So 0.9 to the first power is 0.9. 0.9 to the second power is 0.81. And 0.9 to the third power is 0.729. If I kept going, so let's do 4. 0.9 to the fourth power is 0.6561. It's going to continually just get smaller and smaller. So if I went over 1, up 0.9, 2, 8.1, 3, if you notice, my graph is just going to get smaller and smaller until it does that. And you can't really go below 0 on this type of graph because you can't have nothing. It's just going to get really, really, really tiny. All right, that's it for your notes.